All right, let's go through the problem. It looks like we had somebody that came into the room and must have realized they were in the wrong place after I said that, because they're not there anymore. All right,
No, it was me, Professor. Sorry, I changed my name. It's because I joined my girlfriend's laptop and
okay, okay, just so long as you're in the right place. Okay. All right, so let's look at these. Then I'm going to go back and look at the quiz problem very quickly. And let me just make sure I got the right number of people. 2, 4, 6, 8, 10, 13. Good. Then I'm going to look at the quiz problem and look at the homework problem. And I just realized the homework problem should have been a real challenge because I'm not sure I gave you enough information as I look at it. All right, so the first thing we had to do was we were asked to find IT and REQ. So we need to recognize this is a series circuit. This was a parallel circuit. So for the first one, I need to make REQ is going to be R1 plus R2 plus.
Professor, I don't think it's.
Oh, yeah, I got to share the screen. Hold on. Thank you. Okay, so it's a series circuit and a parallel circuit. So series circuit, it's just the sum of the resistances. So I have 330 plus 2K plus 270 gives me 2,600 ohms or 2.6 K ohms. IT is always VS over REQ. That's valid for series or parallel. So I have 15 volts divided by 2.6 K ohms. $138.5. And if we just do a quick double check, R min is, oh wait, that's just parallel. That, oh, I know why. I think the math is wrong on this. Oh. How about 5.77 K ohms? How about 5.77 milliamps? And then later on, we were asked to find V sub R2 is going to be I sub R2 times R2. The current through R2 is the current in the series circuit. Because it's a series circuit, the current's all the same. So I have 5.77 milliamps times 2K, 11.5. 11.54 volts. And so that's the stuff for, oh, and I sub R3 is equal to IT 5.77 milliamps. If we look at the second circuit, the REQ, since it's a parallel circuit, it's 1 over R1 plus 1 over R2 plus 1 over R3. And we take the reciprocal of that whole mess. So I have 1 over 2K plus 1 over 910 plus 1 over 390. $240.2 ohms. And we see whether that makes sense or not. R min is going to be the least resistor, which in this case is 390. R max is going to be the least resistance, the other way around. Over N, where N is the number. So I got 390 over 3 or 130 ohms. So we know that the range for our calculation has to be somewhere between the smallest resistance, 390, and the smallest resistance divided by the number in parallel, which is 3. So it's got to come out to be somewhere between 130 and 390, and certainly 240 does indeed fall into that category. VR4, because it's a parallel circuit, is equal to V sub S. So that is 12 volts. And then IR5, remember this is a parallel circuit, so it's not equal to IT. Oh, I had to find IT. Let me do that over here. IT is always VS over REQ. So I have 12 volts divided by 240.2. $49.96 milliamps. So remember, that's the current that's leaving the source and going into the circuit. And it splits up. Part of that 49.96 goes into R4, part goes into R5, part goes into R6. That was Kirchhoff's current law. The current entering equals the sum of the currents leaving. Okay? So IR5, we need to figure out, we can do that using Ohm's law, VS over R5. Let me rewrite that as V sub R5. And you'll see why I'm doing that in a minute or later. The voltage across R5 is the supply voltage in this case, 12 volts. That's a parallel circuit divided by 910 ohms. $13.19 milliamps. Okay. Any questions on those two? Just a quick sort of review of series circuits, parallel circuits. Okay. Before I forgot to announce that to my other class. Before I get into the quiz and the homework, let me just see, just a quick reminder. I did speak to Professor Atwood. He is going to proctor the exam during the lab period. So the exam will be Thursday, the 19th, a week from today. We'll cover series circuits and parallel circuits. We are going to start series parallel between now and then. It will not cover series parallel. Series parallel circuits are circuits that have some stuff that's in series and some stuff that's in parallel. So that will not be on. The only thing is straight up series and straight up parallel. Okay. Remember,
Professor,
yes.
would you mind going back for a second?
Oh, sure. You mean back to here?
Thank you.
Yeah. Absolutely.
Yes. 1 second.
Just remember on the exam, if I said to you, like I did today, calculate IR5, you could use Ohm's law, or you could use current division. But if I say to you, calculate IR5 using current division, or calculate IR5 using Ohm's law, you must use current division or Ohm's law as appropriate, because what I'm really saying to you is if I said calculate IR5 using current division, what I'm really saying is show me that you understand current division. And if you use Ohm's law, that doesn't prove anything that you know anything about current division. Same thing with if I did the first circuit, if I said calculate VR2 using voltage division, and you did it by Ohm's law, it doesn't show me that you know anything about voltage division. So even if you come up with the right answer, if I specify a method and you come up with the right answer using another method, it's still going to be marked wrong. Because what I'm saying when I specify a method is saying, show me you understand that method. Okay?
Thank you, Professor.
Okay, you all set? Anybody else need
Yeah.
any more time before I leave this? Okay, so let's look at first the quiz, because I wanted to do that last class. I think Natasha asked about the quiz, although I did give you a solution, so I'm going to go through it fairly quickly. But let me get to, yes. Okay. All right, so the quiz question was, that was the quiz, and I don't remember what I asked you to find. Anybody remember what I asked you to find? Probably RT.
I'm going into the thing right now. If you give me half of a second.
Probably IT. And I probably asked you to find a voltage using, oh, I know what it was. Yeah, that was a problem. Okay. Well, let's do this. REQ, we know that that's R1 plus R2 plus R3 plus R4. So that's 820 plus 1K plus 680 plus 2K. So 680 plus 820 is 1500. 1500 plus 1K is 2500 plus 2K is 2700. Is that right? 3K and 50. Whoa, that's not right. 2K and 1K is 3K. 3K plus 1500 is 4.5K. And IT,
Professor, we're not saying anything writing.
you're right, you're not. So where? There we go. So it's a series circuit. So we we add up the resistances, that works out to be 4.5K. IT is VS over REQ. So I have 9 volts divided by 4.5K. Two milliamps. Okay. Now, did you find the quiz, Natasha?
I'm just logging into the mail. It's taking like a little bit of time. I don't know why. But
Let me see if I can just, if I can pull it up on my computer more quickly.
Okay.
Pull it off my Drive account, and it'll be probably quicker.
Got it, Professor.
Oh, I just opened the responses.
I also have it when you want it, Professor. But it's only showing the grades and stuff.
Okay,
Not
yeah,
the
so I don't need that. I need the actual quiz itself. So let me, there we go. All right, so I asked you to calculate REQ, calculate IT, calculate VR2 using Ohm's law. So VR2 using Ohm's law says that it's IT times R2. So that would be 2 milliamps times 1K is 2 volts. And then calculate VR4 using KVL. I really didn't mean to do that. That was not what I wanted, but I wrote what I wrote. So using KVL. So that means that we know that this is 2 volts. Plus minus. We want to find VR4. So I need to find VR1 and VR3. VR1 is IT R1. So it's 2 milliamps times 820. 1.64 volts. VR3 is IT times R3, 2 milliamps times 680, 1.36 volts. So using KVL, we can say that VS is VR1 plus VR2 plus VR3 plus VR4. We know that VS is 9 volts. VR1 we just figured out is 1.64. And VR3 is 1.36. So we've got going around plus 1.64 plus 2.00 plus 1.36 plus VR4. And when you solve for VR4, you come up with, what is this? This is 3 volts, 5 volts, 4 volts. So that was the quiz. Any questions on the quiz?
Do you mind going over number 2? For the last one, I got that wrong.
Which one?
Because I used for like using KVL because I used the wrong method. I used Ohm's law instead.
Right.
Yeah, so like I got like a point, but like I got it wrong. And then I lost 1 point off of number 2 when you wanted to calculate IT.
Yeah. Okay, so calculating IT in a series circuit, it's always going to be the REQ of the 3 resistors. Think about it this way, whether it's series circuit or parallel circuits, you can think about it this way. Envision that VS, the supply voltage, is connected to some sort of a box.
Mm-hmm.
And inside of that box is a circuit. It could be a series circuit, or it could be a parallel circuit, or we're going to see it could be a series parallel circuit. But the bottom line is that between these two ends, there's an equivalent resistance called REQ.
Mm-hmm.
All right? There's an equivalent resistance called REQ. Now, that resistance, just mark somebody here. If it was a series circuit, we got that resistance by adding up the resistors. If it was a parallel circuit, we got it from the 1 over R1 formula. If it was a series parallel, we're going to talk about how we would get the REQ. But the bottom line here is that we got this REQ. We know that the IT is the current that leaves the source and goes through the circuit. Now, once it gets to here and goes into here, we don't know what happens. It may go in a series circuit into one resistor, out, into one, out, into one, out, into one, or in a parallel circuit, like we saw before, it may split up and part goes to one resistor, part goes another resistor, part goes another resistor, and then recombines at the bottom. Or in a series parallel, it can do a combination of those. But the bottom line here is that something happens, but it comes out with the same amount that it went in with. So if you envision this as a simple series circuit or a simple circuit, simple Ohm's law circuit, we can say that the IT is just going to be VS over REQ. And it doesn't matter whether the REQ came from a series circuit or a parallel or a series parallel. IT is always going to be VS over REQ.
I put that right. I put that down and I got the right answer because that's the answer that we used for like number 4, but you took off a point.
All right, I'd have to go back and look at your quiz because without it in front of me, I can't figure out what I did in terms of grading. But shoot, let me write it down. All right, I'll take a look at it. Okay. Any other questions on the quiz before we leave it? And let's go to the homework, which as I look at it now, I realized I forgot to give you one piece of information. But we can do the first part. I was supposed to give you RT and then instead ask you to find it, which you can't do. All right. So you're told over here that P sub R4 is 9.6 watts. So if we think about setting up that table, If we can't figure out quickly where to start. All right, we're told that R1 is 20 ohms, R2 is 150, R3 is unknown, R4 is 60. We're told P sub R4 P sub R4 is 9.6 watts. And that's pretty much all we know. So we could, if we think about it, we always need at least two things in a row to find anything else. So I could use the 60 ohms and the 9.6 watts to find the current, or I could use the 60 ohms and the 9.6 volts, 9.6 watts to find the voltage. Which would be the better choice?
Voltage.
Repeat the question.
Sure. I could use the 60 ohms and the 9.6 watts to find the current, or I
Mhm.
could use the 60 ohms and the 9.6 watts to find the voltage. Which one would be the better one to choose?
I
The
would use
voltage.
current. I would use current.
All right, wait, we have a dispute.
You
Dispute.
can use the voltage because like you would just square the V square, like V squared over R, like PR4.
Yeah, but
And
why
then
is it better to find the voltage?
Because I mean it might be more like more close to the result.
No. What do you know about parallel circuits? What stays the same? What's different?
The voltage.
Oh, voltage is the same in everyone.
The
And every
voltage is
like
the same
resistor.
in everyone. So if I find the voltage here, I know that's the voltage here and here and here. Okay? So we can find the voltage. That would be the better choice. So we know that P is equal to V squared over R. If I rearrange that, I get that V is equal to the square root of P times R. If I want to get the V by itself, the first thing I got to do is, let me back up one. We all know PEMDAS. And we know that if we're solving a problem, parentheses are the most important. Whoops, I forgot the E. Exponents, then multiplication, division, addition, subtraction. And that's the order we have to do the problem in. If you're rearranging a problem, you're trying to rearrange a formula, you're going to do PEMDAS backwards.
Deep Kiki, my nigga.
What?
Bruh.
I don't know who that was, but totally inappropriate.
Sorry, my cousin just walked in.
All right. We're going to do PEMDAS backwards. That means we're going to get rid of any addition and subtraction. We're going to get rid of any multiplication and division, then any exponents and parentheses. So if I look at it, I have an exponent over here. I have a division over here. So what we're going to do is we need to get rid of the division first. So if we want to end up with the V, the R is dividing into V. So if we want to get rid of division, we counteract that with a multiplication. Whatever you do to one side, you do to the other. And if you're Totally familiar with this. Hang with me. I always find this is a place where people tend to get lost. So I'm just going to go through it. The R's will cancel. Now I've got a power over here, an exponent. The exponent is squaring. So the way I get rid of a square is to take the square root of both sides. So if I take the square root of v squared, that just gives me v is equal to the square root of p times r. Hopefully you all know that. My past experience has been there are people who get lost in this. So I always take the time to go over it. So v is equal to square root of p times r. So I have 9.6 watts times 60 ohms. And when we do that, we get 24 volts, I think.
Professor?
Yeah.
Oh, never mind. I was gonna
Say that again. I have you twice. Oh, there we go. All right. I had asked you to find R3. Somewhere along the line, I forgot to give you IT. Actually, I asked you to find IT, so you can't solve it for those other two. So if you struggled with it, I apologize. But I meant to give you the value of IT, and somewhere along the line, asked you to find it instead of giving it to you. I think what happened is I was going to give you IT and P. I guess that what it was, and then ask you to find R3. But anyway, that is. Okay. Any questions on how we found the voltage?
Mm-mm.
And V1, remember, in a series circuit, that's equal to V2, parallel circuit equal to V3, parallel equal to V4, and also equal to V sub S. Okay, let me go back to the screen I was going to use before. Okay, I already talked about the quiz, so let's do a new sheet. All right, series parallel circuits.
Wait, Professor.
Yeah.
Are we not finding the R3 and the I sub T for the homework?
You can't. You don't have
Oh,
enough
okay.
information. I mean, even if you, let me go back to that a minute. I'll show you why. Like I
Okay.
said, there was, I switched what I was thinking about doing midstream and ended up making the problem impossible to solve. So we figured out that this is 24 volts. This is 24 volts. This is 24 volts. Oh, you can. Never mind.
You can look for it by looking for IT, like the
Yeah, but you
Kirchhoff
can't.
law.
Yeah, but
Like you calculate IR3, IR4, and like for
you
the
can't
I.
find. The problem is you can't find IR3. So you could find IR2. If you divide 24 by 150, you get this. If you divide 24 by 20, you get this. 24 by 150, you get this. 24 by 60, you get this. The problem is for R3, you know this is 24 and that's it. For IT, you don't know the I, you don't know the R, you don't know the P. So you got in the column for current, you got two unknowns. You've got the R3 as a question mark, the IT is a question mark. So you can't solve for
Okay.
IT because you don't know R3. You can't solve for R3 because you don't know the REQ. So the bottom line here is I didn't give you enough information. I meant to give you the value of IT. If I had given you the value of IT, if I had given you this value, then you could have solved for this value. And once you had that value, then you would have been able to solve for R3 and you would have been able to find REQ. Okay? But because of the fact that I didn't give you, I was going to give you that and then changed my mind what I was going to do and ended up not giving you what you needed to solve the problem. So that's why I said that we can only go as far as we did.
I got up to 24 words. It was kind of hard to find the R3 and the ISFT. Thank you so much for going over.
Yeah, I was just going to say, because that was impossible to solve for it. Like I said, midway through, I changed my mind what I was going to ask for, and as a result, it happened. Let's go to series parallel. Series parallel, which, so I don't have to write series parallel all the time. I'm going to just abbreviate as S-P. All right. So a series parallel circuit is a circuit which contains some elements in series and some elements in parallel. And I'm going to call them elements because, you know, this is a resistive circuits course, but everything we're doing here applies not only to resistor circuits, but next semester you're going to see resistors, capacitors, and inductors connected sometimes in series, sometimes in parallel. That is where we say, you know, it's an element, because everything we do here is going to apply to the AC circuits course next semester. So for example, if I had a circuit like this, if you look at that, you say, well, I'll give you a minute to jot the circuit down before we talk about it. Let me do it that way.
Do we know what the voltage is, Professor? Or
No, I'm just talking in generalities here.
Okay.
So let's look at this circuit and let's think about it for a minute. We know that IT leaves the source. And where does it go? What's the first thing it hits?
R1.
R1. So the current goes into R1, comes out of R1. The current that comes out of R1 goes where?
Into R2.
R2.
Into R2. So what do you know about R1 and R2?
Series. It's in series.
R1 and R2
They have the same current as
have
well,
the
right?
same current, so they're in series. But now what happens when it gets to this point right here?
It splits up
It
into R.
splits.
Yeah.
Part goes through R3 and part goes through R4. Okay? So maybe R3 and R4 are in parallel, but we don't know that yet. The current that comes out of R3 is now, remember, trying to get back to the negative of the source, so it's going to go that way. The current that comes out of R4 is going to go back, and here, these two recombine. So they recombine to become IT again. So we'll just say that the recombined current goes into R5, comes out of R5, and goes back to the source. So in reality, since R5 also has the same current, R5 is in series with R1 and R2.
Mm-hmm.
Now, we need to check on R3 and R4. Let's do it this way. If I call this point A, call this point B, call this point C, call this point D, and call this G for ground, because in multisim we'd have to put a ground there. If I made a list of the resistors, and we said, what nodes does it connect to? Well, R1 connects, one end is A, the other is B. R2 connects between B and C. R3 connects between C and D. R4 connects between C and D.
Hmm.
R5 connects between D and G. So if I look at it, these two share a common node, B, but have different nodes on the other end. So these two are in series. These two share a common D and C. So they have two common nodes. They're in parallel. Okay? And this one we need to know is in series only because the current's the same. But what I wanted you to spot was, if there's a question, you can always make up the list of the resistors and see, do they have one common end or do they have two common ends? If they have two common ends, they're in parallel. If they have one common end, they're in series. Everybody with me on that? Questions?
I have a quick question.
Yeah.
So the one that goes to from D to the R5, that's going to be E, right? From
Well,
D to
no.
R5?
No, think about it this way. Remember we talked about nodes the other day, and I said I can go from a spot up to here, and then we go back, and that would be a node that we call A, and this would be a node we
Oh,
call
okay.
B, and this would be a node we call C, but remember that goes all the way over, crosses over, comes back. We did that the other day. And then D, if I wanted to start here, I would go this way. Then I get to the resistor, I turn around and come back. I go over to here, I get to this resistor, turn around and come back. Get to the resistor, turn around and come back, and I'm back where I started. So all of this is node D. And if I start over here with this resistor, I go along, I get to the battery, I turn around and come back. Get to the resistor, turn around, and I'm back where I started. So all of this is, I just labeled it G for ground, because remember
ground.
in multisim, we'd probably put ground at the negative end of the battery.
Okay.
So I called it D instead of G instead of E.
Okay. Thank you.
Okay, that clear up?
The only question that I was gonna have is, would you just have R5 noted as D because you were not supposed to mark it as ground?
Right, we would label it if I was talking about voltages, I would
Mhm.
might talk about VAB, VBC, VCD, VCD, because they're in parallel, that was two of them be the same, and then VD as the second subscript not being written as, because it's defined to be as ground if there's no second subscript.
So, but the reason that you have it as G for right now is just for note purposes?
Yeah.
Okay.
Anybody need any more time with this before I put up another circuit?
Mm-mm.
Give me one more second.
Okay.
Thank you, Professor.
Okay. So let's say I had something like this. Take a minute and see if you can determine what's in series and what's in parallel. What resistors are in parallel? What resistors are in series?
You want us to tell you?
Well, we're going to go over it, but just mentally or jot it down on a piece of paper so you remember. Anybody have any ideas?
Can you give us like 2 more seconds, please?
Sure. Okay, anybody have ideas?
Yeah, do you want us to start like, we could start labeling it off. Like on the side, I would put R1, R2, all the way down to 7.
Okay, so let's cut straight to the chase.
Mhm.
What, give me one example of something that's in series or parallel.
I think R2 and R3 in parallel.
R2 and R3. So Jancy, you said R2 and R3, and I'm going to shortcut this. All right, anybody else have an idea about any of the other resistors?
I think R4 is parallel to both R5 and R6 together.
Okay, so I knew that was bound to happen. At this point in time, we're not going to talk about together. We're
Oh,
going to talk
okay.
about individual resistors. So what individual resistors are in series? You're absolutely right. It is in parallel with the combination of the other two. But for now, I just want to be able to go through and say these two are in series, or these two are in parallel, or these three are in series, or whatever. So what else have we got?
Is that R5 is in series with R6?
R5 is in series with R6.
And R1 and R3 are in series.
R1 and R3 are in series. All right, let's go through and see whether that makes sense or not. Any other combinations before we go through it?
You said R2, R3, and then R5 and R6. I think that's it.
Okay, so let's look at it first from the current viewpoint. If I talk about IT leaves the battery, goes into R1, comes out of R1, and what happens when it gets to here?
Does it split into R2 and R3?
It splits between R3 and R2. So if it splits, can the current in R1 and R3 be the same?
No.
No. So we can't say they're in series. We put that one out since I sub R1 does not equal I sub R3. Okay? Everybody agree with that? So then the current
Can you
goes out
repeat
of
that one
R.
more time? I'm sorry.
Say that again?
Can you repeat that one more time? I'm
Sure.
sorry.
Sure. We know that IT leaves the battery, goes into R1, comes out of R1, but when it gets to this node right here, it splits. Part goes to R3 and part goes to R2. So that means that since only part of the current that went in goes to R3, the current in R3 and the current in R1 aren't the same. All right, IR1 does not equal IR3. And what's the rule for a series circuit? things are in series, the currents have to be the same. So that means that this is not in series with this. It turns out that we're going to see later on, we start to do some stuff, that the R1 is in series with the combination of R2 and R3, but it's not in series with R3. It's not in series with R2 because the currents are the same, different. It's not the same current in R2 and R1 or in R3 and R1. So the current leaves R3, current leaves R2. Those two combine to get back to IT over here. And what happens when it gets to this node?
It
It
splits.
splits again. So part of it's going to go through R4 and part of it's going to go this way. Now, what happens over here? Current goes into R5, comes out of R5, goes into R6, comes out of R6, and goes that way. So what can you say about the current in R5 and the current in R6?
It's
They're in
the same, right?
series, okay?
Yeah, series.
And we can say that because IR5 is equal to IR6. Current that goes into R4 leaves R4, and now when we get back to the junction over here, these two combine again to get IT. IT goes into R7, comes out of R7, and goes back to the battery. Does everybody follow why we talked, when we talked about the current, why R1 is not in series with either R2 or R3, and why R5 is in series with R6?
Yeah.
Okay, everybody follows that?
Yeah.
Yes.
Okay, so Natasha mentioned before we could make a list. So if I make my list, R1 connects between node A and node B. R2 connects between B and C. R3 connects between B and C. R4 connects between D and, C and E.
Yeah.
All right, connects between C, this is all node C, and E. R5 connects between C and D. R6 connects between D and E. And R7 connects between E and G. So if I look at it and look for commonalities, I see these two share two common nodes. So these two are in parallel. Okay. 5 and 6 share a common node. So these two are in series. Okay. And if
What
you
about
want to, if you
what about
want
one and two?
to,
They have some same node number B.
I didn't, you say that again, you got garbled in it.
Right. Number the resistor 1 and 2, they have same node B.
Here.
Yeah.
Yeah, I was just going to get to that. If I look over here, we can see that this resistor R1 shares a node with this common term here. So R1 is in series with the parallel combination of 2 and 3. But it's not in series with R2, and it's not in series with R3. It's in series with the parallel combination. All right. So we know that it's not in series because the currents don't match up, but we do know that it is in series. We're going to know later that this resistor is in series with this parallel combination. The same way that we're going to know later on that this resistor R4 is in parallel with the combination of 5 and 6. Okay, which we'll talk about when we get a little bit further. All I wanted to do today in introducing series parallel is to get you to start thinking about how do I look at a circuit and how do I figure out what's in series, what's in parallel. We got two things we got to consider. One is what happens with the current, and the other is what nodes the things connect to.
Professor,
Yes.
let's say you have IT, right?
Yeah.
And you have one of the current values for one of the resistors of R2 or R3.
Mm-hmm.
You find the other one by like subtracting it or something like that.
Absolutely. Kirchhoff's current law works at any node. We used it in a parallel circuit, but it works at any node. Current that goes in equals the sum of the currents that leave. Okay, so whatever current I had here, that splits to become IR2 and IR3. So we could write KCL as IT equals IR2 plus IR3. Yeah, we could do that, and we will do that later on. Okay, let's do one more before we call it a day. Let's say we had take a minute, see what's in series, what's in parallel. Oh, I forgot Antonio would yell at me. What's individual resistors are in series and what individual resistors are in parallel?
You said don't talk about anything that's together right now.
Yep.
Okay.
Any ideas?
Can we have half a second, please?
Sure.
Are we doing the same thing, trying to figure out what series and parallel?
Yep, you're just trying to figure out what individual resistors are in series, what individual resistors are in parallel.
So R1 and R2 in series.
1 and 2 in series?
R1 and R6 are in series.
I'm not really seeing.
Oh no, never mind. I didn't see R5.
I guess you could say R1. I think R1 and R2 are in series.
Nah, I don't think so.
No, sir. R1 and R6 are in series.
R1 and R6 are in series. All right, let's do it because I just looked at the clock. All right, let's talk about it from the current viewpoint. IT leaves here,
Mm-hmm.
goes into R1,
Mm-hmm.
leaves R1, and what happens when it gets to here?
It splits to R2 and
It
R5.
splits to R2 and R5. The minute you say the word it splits to,
No longer.
whatever it splits to cannot be in series. So R2 can't be in series with R1. R5 can't be in series with R1 because they have different currents. Let's take a look at this current. Current goes to here. What happens when it gets to here?
It splits to R3 and 4.
It splits to R3 and R4. So we know that R2 is not in series with R3 and it's not in series with R4. The current that goes this way, the current that comes out of R3 goes over to here. Current that comes out of R4 goes over to here. Current that goes into R5 comes out of R5 and goes in this direction. At this point, these two combine to form one bigger current. And at this point, the current that came this way and the current that came from R3 combine, and those two combine to form IT.
If that's the case, then it doesn't seem like anything is in series with each other individually.
So no resistors.
But you have some parallels if you combine.
No resistors are in series. Okay, no individual resistors are in series. Let's put nodes on it. So we go along the edge, we get to the resistor, we jump back and turn around, go back. We get to the source, we turn around, we come back. So all of that's node A. If we start over at the other end of the resistor, we go along the side, we hit the wire, we turn, we get to the resistor, turn around and come back. We turn, we get to R5, we turn around and come back. And we go along there. So all of this is node B.
Mm-hmm.
If I talk about 2, we go down, we hit the resistor, we turn around and go the other direction, along the wire, down. Here's the resistor, we jump back, turn around, get to the wire, we turn, hit the resistor, jump back, call all this node C.
Mm-hmm.
If we start over here, we go along the edge, we turn, cross the wire at the component. Remember, the only time we cross a wire is at a component. All right, now we turn, we hit the component, we cross the wire and come back the other direction. We go along here, hit the component, cross the wire, turn around and come the other direction. We go all along here, we turn to follow the wire. Now we're up to R5, we jump over, we're back where we started. So this is node D. And then if we go along here, we hit a component, namely the battery, turn around and come back. Along, turn around and come back. So this is node G. So if I look at my resistors, R1, R2, R3, oops. R4, R5, R6. R1 goes between A and B. R2 goes between B and C. R3 goes between C and D. R4 goes between C and D. R5 goes between B and D. And R6 goes between D and G. So we figured out already that no individual resistors are in series. Okay. So no individual resistors are in series, but are there any that are in parallel?
Mm-hmm.
Which?
So
R2 and 3.
in parallel would be R3 and R4.
Yeah. Both share a C, both share a D. So these two are in parallel. And it was a pretty easy spot because they were drawn parallel to each other. Okay.
And then
But I could have drawn this way. So this is R2. This is R3. This is R4. And R5 was over here. All right. So if I had drawn this section of the circuit this way, it might not have been as obvious that 3 and 4 are in parallel. Here they're drawn parallel to each other. But if I drew it this way, electrically, if you went through and looked at the nodes, they both still connect between C, this node, and D, this node, except they're not drawn parallel. So you always have to go back and look at the electrical connections, not how it physically, is it vertical, horizontal, are they both vertical, both horizontal? On the drawing, you got to look at the electrical connections. Okay?
Mhm.
All right. Questions before we call it a wrap?
Couldn't you also say that R5 is like parallel to the combination of R2, 3, and 4?
Parallel to the what?
Parallel to the connections in R2, R3, and R4. So it's technically
Operative word to the combination. We're not talking about combinations yet. Yes, you're right. They are. But I want to just, for today, I just want to stick strictly with individual resistors.
okay.
Because if you don't see how the individual resistors are connected, what's going to happen is you're going to make combinations that maybe aren't combinations that you thought they were.
Okay.
So I'm just trying to stay simple today. The confusing part will come later.
Okay.
All right. Other questions? Okay.
Yeah, I don't know if you said this, but about the exam, are you going to have another review class like you did before?
I could do that. I will send out a blurb, not a blurb, a poll to see what time is the best time. And that reminds me, I have to do another poll for the other class.
By the way, Professor, do you happen to have any idea when we'll have our final exam? I'm asking because I have to take time off of work because I want to make sure that I have time to like study and stuff.
Yeah, let me look at the calendar. I'll get back to you tomorrow, next class.
Okay.
All right.
Yeah, I should have asked you earlier because I need 30 days notice, but that'll be fine.
Okay. I will
Can
try and, if I look at a calendar, I'll probably send that in. And I got to talk to Atwood too to see if he's going to proctor it or not. Once I find out, I'll send an email out.
Okay.
All right.
Can I ask you something like unrelated to class, like in regards to the quizzes and stuff?
Sure.
I remember we were talking about like the quizzes and like the tests and stuff. So I sent you an email about what like the stuff that I lost points on.
Oh, did you? Because I haven't gotten that yet. When did you send it?
I just sent it during class, so I just wanted to see if you got it.
Yeah, I'll respond to that.
Okay.
Oh, before I forget, figure on Tuesday being a quiz on series or parallel, individual series or individual parallel circuits. Okay, so a quiz on Tuesday. Let me put that up back under announcements.
Test Thursday and is getting proctored by Professor Atwood, right?
Yes.
Okay.
So quiz Tuesday, 11/17.
So are we gonna attend class or are we just gonna have it during the lab period like last time?
What do you mean attend class?
Like the last time we had the exam and Professor Atwood proctored it, it was that we took class normally and then we went to campus to take the test. So I'm asking, are we gonna have a normal class and then go to campus and take the test? Or did we, okay.
Yeah. Yep.
Once a review that I'm the chair, you got
Say that again? I missed what you said. All right, so Tuesday there'll be a quiz on either series circuits or parallel circuits, or maybe both. You should be comfortable with both. And then Thursday is the exam. Be good, like a good brush up for the exam on Thursday. All right, if there are no questions, then have a good weekend and talk to you on Tuesday.
Thank
All right,
you.
have a good one, Professor.
Take care.
Oh, wait, are we in person for lab today?
Yes, sir.
I believe so. Yep.
All right. Thank you.
No, I would don't like this online shit.
I mean, but like,